Today's lecture 27. We're going to start with a business optimization example and do something that I did talk about a few weeks ago, something called sensitivity analysis, which we're trying to look at how the answers depend on the parameters. And to me, it's really the most useful thing about optimization is doing sensitivity analysis. And I'll try to emphasize why. We'll do more differential equations in slope fields, including in lecture B something called second order differential equations, which come up mostly in physics. And then finally, we'll do again related rates problems. All right, so here's our business optimization example. Suppose you're talking about a ferry boat that carries passengers and has lots of costs, fuel costs. Other kinds of costs include just maintenance and repair and the staff that you have to hire. It says the cost of fuel to propel a boat through the water in dollars per hour is proportional to the cube of the speed. Okay, so as the speed doubles, for example, that means your fuel cost goes up by 2 cubed, 8 times as much. Evidently, this boat is very inefficient. Okay, you go too fast, you're going to use a lot of fuel. A certain ferry uses $80 worth of fuel per hour. So I've got an arbitrary parameter here. This is taken from the book. I'm going to assign this problem, but you're going to have particular numbers, like we've been doing recently. You're going to have a particular number for A. I think it's $100 worth of fuel per hour when cruising at 10 miles per hour. But then again, we have these other costs. Apart from fuel, the cost of running the ferry, labor, maintenance, and so on is B dollars per hour. I think in your problem it's $675 per hour. If I'm remembering correctly, we'll look at it in another slide actually. The question is, at what speed should the boat travel so as to minimize the cost, not per hour, but per mile travel? Okay, now that's going to be, if you are running a ferry and you are just sort of cruising around the lake, you don't have a certain destination in mind, you'd probably prefer minimizing the cost per hour in that situation. However, if you're going from one destination to another, a certain number of miles, then you'd probably prefer minimizing the cost per mile, if it doesn't matter how long it takes you to get there. And this reminded me of the ferry that I rode back 8 years ago. This is the Staten Island ferry. My family went out to New York in 2011. And it's actually free for the passengers. Okay? It's covered by New York taxes. Visitors, tourists can ride it for free. New Yorkers ride it for free technically when they actually ride it, but they have to pay for it with their taxes. It goes back and forth between Manhattan and Staten Island, which is close by. All right, so how do we actually do this? Solution of the ferry problem. We've got to think in terms of units. That's the best way to try to come up with a formula for the function you want to minimize. The sources were giving us costs in dollars per hour, but we want to translate that, transform that to cost in dollars per mile. And the key thing to think about are those units, and the fact that we're thinking about the speed of the boat, which would be in miles per hour, and a way to get from here to here, in terms of the units at least, is to divide by a speed in miles per hour. Why? If you're just thinking of it in terms of units and unit cancellation, you've got dollars per hour divided by miles per hour. The hour units are going to cancel and give you dollars per mile. So what we're going to do is, again, we're going to take those hourly costs and divide by the speed in miles per hour. And that will convert the speed, the cost to dollars per mile. Like I have it. Here's another key. The fact that the fuel costs were proportional to the cube of the speed. And we had a certain, let's go back there, we had a certain cost, $80 per hour when going 10 miles per hour. That's going to give us an equation that's going to help us solve the problem. Here it is. Remember, this is the cost in dollars per hour. It's proportional to the cube of the speed. 10 miles per hour is the speed at which it's going to cost $8 per hour. K is the proportionality constant. So A is going to be K times 10 cubed. 10 cubed is 1,000. So this becomes 1,000 K. And that allows you to solve for the constant k, which then allows you to write the fuel cost in terms of A in the most accurate way. Here's what I mean on that. Again, like I have on the board, because dollars per mile is dollars per hour divided by miles per hour, the cost C in the units we want, dollars per mile, is going to be the cost of fuel in dollars per hour divided by the speed. I'm using this principle here, taking the cost in dollars per hour and dividing by the speed to get this. And this coefficient here comes from the previous one, A over 1,000. The B was the other costs, like for your maintenance and staffing. It was given in dollars per hour as well. That makes sense. You gotta, when you hire staff, you gotta pay them in a certain number of dollars per hour. So B is already in dollars per hour divided by the speed. This will also be in dollars per mile. The sum of those two are the total cost. Again, in dollars per mile. And then you simplify a little bit. This V can cancel with one of those V's to leave a V squared there. And this can be written, V over V is the same as V times V to the negative 1, which is a little bit more convenient for differentiating. So now do the same thing we've always been doing. Find the derivative, set it equal to 0. See if it is a min or a max, right? We got to use either the first derivative test or the second derivative test to see if it's a min or max. It might be neither, right? You can have functions that have critical points where it's neither a min or max. We talked about that last week, like the x cubed function. Has a critical point at 0, horizontal tangent there, but on some interval around 0, it's neither a min or a max. You have to use one of those tests to verify it's either a min or a max. And in this case, we want it to be a min. Again, when you've got parameters, the second derivative will probably be easier to use, the second derivative test. But first, find the critical point, the derivative of this cost with respect to the speed, the derivative of f. Just mentally compute it here. We've got to bring down this 2 in front. 2a over 1,000 is the same as a over 500. And then we bring this negative 1 down in front. We get a minus sign here, minus b times v to the negative 2, which is what you see there. Set that equal to 0 and solve for v. Separate into two fractions on two different sides of the equal sign. Cross multiply is what I did. I did a few steps there. And then take the cube root. Okay, so it seems like a lot of these problems have had a similar feel. We end up taking a square root or a cube root at the end. And that can be written in this way. Okay, so that's the critical point. It does depend on these constants, a and b. Which, again, as I do the problem, I think of those as being constants. But notice I'm also emphasizing that I could think of them as variables. In the sensitivity analysis, we are going to think of those things as variables. That's the most useful because that tells you how those costs, the A and the B, affect the answers. Okay, and if you think costs are going to change, if you think A and B are going to change, because, for example, maybe your employees are going on strike, they want more in hourly wages, that can help you assess how your critical speed, V, and the minimum cost change, and help you make decisions. So it's really useful. Here's the second derivative. It's always positive, so it's really a global min when V is positive. The second derivative test only tells you about local minimum and maximum. Okay? If the second derivative is positive, you've got a local min near the point. If the second derivative is negative, the graph is concave down, you've got a local max. But in reality, you really could extend those tests to global minima or maxima. If, for example, you know the second derivative is always positive, the graph is always concave up over the entire domain, at the critical point, it's got to be a min. Global min. Again, take that critical point and plug it back into the original function. That's what I mean when I write this. That's the original function. I'm plugging the critical point back in terms of A and B. It's going to give me my minimum cost. Kind of a tricky calculation. I skipped some steps. Again, this is one of those things that would be good for you to check after class to make sure you could do those steps. Again, these problems are perhaps too complicated to put on exams, but they do help you understand the homework better. And on the exams, you'll be able to have problems where you actually have numbers involved for the most part. Probably if I do give you something involving parameters like this, I would maybe tell you the answers and you just have to do them, like in these next few slides I'm going to show you. Can I clarify anything there? That's your minimum cost in terms of A and B. And you can plug numbers in for A and B, which I will do here. Let's talk about the sensitivity analysis now. Very important kind of application. Again, to me, as far as optimization goes, this is the most useful thing in real life. How sensitive are the solutions from the previous slide of the Ferry problem to changes in the values of the parameters, the A and B? A, again, related to fuel costs. B, related to other costs. Partial derivatives help give the answer. Find the rate of change of both the critical point for V and the cost for C, that min cost. Find the partial derivatives of those formulas from the previous slide in terms of A and B. For example, here again was the critical point. This was the speed to go to minimize your cost. That's what this means. Get that? That's what this is telling you. This is the speed to go. V is a speed, a velocity, if you're just traveling in one direction, say, to go, that's going to minimize the total cost, both fuel and other costs. 500 to the 1/3 turns out to be about 7.937. We can now differentiate this with respect to either A or B. And here's why I do it. Here's the answers. Again, in your mind, double check that you can do it. Differentiate with respect to A first. You've got a negative 1/3 power there, so you have to bring the negative 1/3 in front and subtract one from that exponent to get negative 4/3. And there's the negative 1/3. And that approximates to this. Differentiate with respect to B, treat the A as constant, bring the 1/3 power here out in front without a negative sign, subtract 1 from 1/3, you get negative 2/3. And that turns out to equal approximately that. Now, how do you use this? Again, in the book's problem, and I did pick the numbers correctly, if I remember them right. A was 100. A was relating to the fuel costs. And B was 675. Those are costs in dollars per hour, not dollars per minute. Those are the things we have to divide by B. This was also related to the B cubed. What happens if you plug those numbers in to these partial derivatives? What do we get and how do we interpret it? If you plug in A equals 100, B equals 675 into the partial of B with respect to A, you get about this value. Actually, you get exactly that number, it turns out. But I had an approximation symbol there, so I kept an approximation symbol there. Negative 0.05 miles per hour per dollar per hour. Units of velocity per unit of cost in dollars per hour. Right? V is a velocity. A is a cost in dollars per hour. On the other hand, the partial derivative with respect to B, when I plug in the particular points, gives you about this. What do these things tell you? They're telling you how your minimum speed depends on changes in A and B. For example, suppose B changes by 10, right? Your employees go on strike, demanding more hourly wages, and you probably would go up by more than 10. Let's just keep it at 10. Say that cost in dollars per hour for the wages and maintenance, et cetera, goes from $6.75 per hour to $6.85 per hour. Then delta B would be 10. And what would that mean about your minimum speed? What is the change, not in the minimum speed, but the speed to go to minimize the cost, is what I'm trying to say. What's the change in the critical? Use that approximation on the screen. It's about 0.007, looking at the bottom of the screen, miles per hour per dollar per hour times the change in B. 10, that was in dollars per hour. And that's going to give you 0.07 miles per hour. Not very big change, but it is a change. That's telling you if your cost increased from 675 to 685, you should increase your speed a little bit to minimize your cost by that much. not much, not really noticeable. Perhaps you're not actually able to manage that kind of small change, but if you could manage that small change, you want to increase your speed by that amount to minimize the cost. It would be more significant and maybe more realistic if I made delta V equal to 100, and then this would be 0.7 miles per hour, which is maybe slightly noticeable. Though again, they are approximations, so to get the perfect answer, you use the original formulas. But these are still useful to think about. They give you sort of rules of thumb for one thing. How about the minimum cost itself? There's the minimum cost formula again. Turns out to be approximately 0.189, 8 to the 1/3, b to the 2/3. I can once again take partial derivatives with respect to a and b. There they are. Just mentally check it again. The partial with respect to a, I treat the b as constant. I need to bring the 1/3 out in front. The 1/3 and the 3 cancel, so you don't see a 3 there anymore. 1/3 minus 1 is negative 2/3. Turns out to be approximately that. And partial with respect to b, I bring the 2/3 in front. 2/3 times 3 is 2. 2/3 minus 1 is negative 1/3. Turns out to be approximately that. And once again, I can plug in numbers. Same numbers as before. So what is this telling you? This is telling you how your minimum cost is affected by changes in a and b. And both of these partial derivatives are positive. On the other slide, there was one that was negative. Maybe we should go back to that slide in a minute here. That's telling you if A increases or B increases, the minimum cost is going to increase. Even if you adjust the velocity appropriately, your cost is still going to go up. That should make sense. A and B themselves are costs. So, which one, here's another thing. Here's something useful. Which one affects your cost more? Changing A or changing B? Changing A does, because this partial derivative is bigger than that. A, the fuel cost, small changes in A has a bigger effect on your total cost than small changes in B. Fuel cost, for the same small increase in either A or B, those fuel costs or maintenance, again, salary costs in dollars per hour, for small changes, equivalent small changes in either A or B, A has a bigger effect on your minimum cost. That's really cool. It's telling you something useful. Do you know? Okay. And so maybe you try to make other adjustments in your life. Maybe you try to see if you can figure out ways to affect the fuel cost. I mean, maybe it's not possible. Buying a more efficient engine would do, I suppose. But that could be very costly as well. Let me go back to the other slide again. One of these was negative. Now this one. That's telling you if A increases, if the fuel costs increase a little bit, that's negative. You should actually decrease your critical speed. A little bit. Okay? Just makes intuitive sense, I suppose. It is still related to the other cost though as well. Can I clarify anything there? If you're just trying to get the big idea and realizing, yeah, I could go back and plug in those numbers in myself and check everything if I wanted to, and you probably should, okay? I don't say that just to say it. It's going to be worthwhile for you to go back and check these things. I do need to still put this in the folder. I'll do that after class. By the way, just a quick aside, I did still not have time this morning to write up the assignment due Wednesday. I'll get that up between 2 and 3. All right, let's go back to differential equations and slope fields now. I just gave you the basic idea of what a slope field was last time. Let's be a bit more precise now. We make slope fields for differential equations of this form. dy dx equals f of x1. Though I will say, I will emphasize the choice of the variable names is irrelevant, right? It could also be dp dt, and of course the function name is irrelevant too. dp dt equals g of tp, that would be of the same form. as what's on the screen. Okay, so the variable names and the function name doesn't matter. What matters is it's the derivative of some unknown function of a certain variable, in this case x, on the left side, and the right side is some expression that just depends on x and y. The dependent variable y and the independent variable x. At every point in the domain of this function, and this is really a multivariable calculus function of two variables here. For the differential equation, y is the dependent variable and x is the independent variable. But for the function f itself, you can think of both variables as being independent variables. That function, multivariable calculus function, has got some domain in the xy plane. Maybe it's the entire plane. That's certainly the easiest to think about. But it could be some subset. That would be the domain of that function, where you're not dividing by 0 and you're not taking the square roots of negative numbers, for example. That could happen as well. For every point in that domain, no matter which point you pick, I'm calling the specific point x0, y0. And you can do this for any point in the domain. Draw a little line segment centered at that point, whose slope is equal to the value of f of x0, y0. And maybe at this point, this value happens to be 2. If it does, then draw a little line segment with a slope of 2. So that line segment centered at this point, its slope is f of x0, y0, which I'm pretending is 2. Now do that for every point in the plane. All infinitely many points. Of course you can't, right? You can't do that infinitely many times. Computers can't even do it infinitely many times. Do it for some finite grid, and imagine doing it for the other points. You're going to get a bunch of little line segments with a bunch of different slopes. If I pick some other point, I'm going to get a different slope, maybe negative. The point is this. Here's the key bullet point. Every time a solution curve passes through any given point in that domain, the little line segment that you drew at that point will be tangent to the solution curve. The little line segment you either drew or could have drawn. Why? It's the meaning of the differential equation. This is essentially saying, find a function, y is a function of x, whose slope at every point is given, or slope at any given point is the value of this function at that given point. In terms of this fixed point here, I could use this notation. I could write dy dx evaluated at the point x0, y0 equals f of x0, y0. This is true for any given point in the domain. Let's take an example. dy dx equals 2x minus y. Then, for example, we could plug in the point 0, 1. X is 0, y is 1, use that formula, and you get 0 minus 1 is negative 1. So at this point 0, 1, I'd want to draw a little line segment with the slope of negative 1. And then do that kind of thing over the entire plane, or have the computer do it to generate a picture like this. There's the particular point, 0, 1, that black dot there. The computer didn't actually draw a line segment through that point, but it drew some line segments close to it. Zoom in on this picture if you need to. You can see these little red line segments close to it do have a slope approximately negative 1. The slope of this solution curve in blue, this is a solution curve, at that point is negative 1. The derivative of the blue curve at that point is negative 1. Its tangent line has a slope of negative 1. And anytime the solution curve passes through the center of one of these little line segments, that line segment will be a tangent line to the curve. It's close right there to being on the curve. It's pretty close right about there. This solution curve has to look like this. It has to follow the slope. Actually, there's a Christian analogy to this. The slope field is like God's law. And the solution curve is like Jesus, okay? It's following God's law perfectly. Perhaps for different initial conditions, all right? I mean that just as an analogy, okay? And if we were to approximate this, it's like us, you know, we can't approximate very well, at least. For large delta x's, we try to approximate the solution curve with like some line segments stitched together. But we fall short, right? We can't match the solution perfectly. What do other solution curves look like here? Again, follow the slope field. We've got one that starts over here, say, it's got to go down this way, and then you do something about like this before going back up over here. Something interesting to note here is there are a bunch of line segments that have a slope of 0. Here, 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 etc. All those little line segments are centered where this is 0. In other words, where y equals 2x. A line to the origin with a slope of 2. Along that line to the origin with a slope of 2, the line segments are horizontal, and solution curves have minimum. That's interesting. Wouldn't be something you would expect without actually making a picture. All right, let's take our break.